Yeah, thanks for inviting me. It's really nice to be here in London. As you already said, I'm going to talk about equivariant and coordinate-independent neural networks. So in general, what is a convolutional network? This means you have a signal on some kind of space or manifold or graph. In our case, we are looking at either Euclidean spaces or manifolds. And then if you are on a manifold, then there's no canonical coordinate system. And we need to make sure that whatever you're doing there has to be independent from the choice of coordinates you use to describe your convolution operation. And the equivariance part just means that if your manifold has a certain symmetry, like for instance, if you have a sphere, you could rotate it, then your convolution operation should commute with this symmetry group action. Yeah. So just to give a very short overview, in machine learning, we always have some input and we want to end up with some prediction. Like here in this task, you would do a segmentation of the cell boundaries. And we do this by optimizing some machine learning model. But as you see in this example already, you have some translational symmetry. So if you shift your input image, then also your output should shift. But you have actually more symmetries like rotations or reflections, which should be preserved. So formally, we have a group action on the input and output space, and these could actually be different group actions. And we want that the machine learning model commutes with these group actions. So going in this direction and then down here should be the same as first transforming your input and then feeding it through the model. And this is what is called equivariance, that this diagram commutes. And if we are looking specifically here at neural networks, these are, at least if they are feed-forward networks, sequences of layers or functions. And we are designing a network which is equivariant as a whole, just by designing the individual functions as equivariant functions, and then by induction, the whole thing will be equivariant.
So are these local or global transformations?
In the first part of my talk, I will talk about active global transformations. And then I will look at the passive transformation viewpoint, which is like you don't transform your image, but your coordinate system, but still global. And then I will come to the local part, which you actually need on manifolds. So we will see both viewpoints. All right, and we will specifically look at convolutional networks. And the convolutional network is basically an MLP, or it has linear operations. But then if you demand, for instance, translational equivariance, you end up with a convolutional network. So you can derive convolutions from translation equivariance. And if you look here at the left, you see a fully connected MLP, which is processing an image. And then these neurons don't really have a spatial structure or don't know anything about the image topology. But you can choose a local connectivity, which is actually what we also have in our retina. And then you will get that the features are also associated to a certain location in the input image. So your features will also be structured with the same topology as your input space. But there's still no equivariance. And to get equivariance, we have to share weights over different spatial positions. And this is then a convolutional network. And what you see in the bottom right is, again, this commutative diagram, which says that a transformed input convolved is the same as first convolving and then transforming your feature map. And what we are interested in is having more symmetries, like what happens if you rotate or reflect your image. And you will also still have the translational weight sharing, but in addition, a weight sharing over these additional symmetries. So for instance, if you have rotational symmetries, then your kernel itself gets constrained in a certain way. So you see this kernel has a certain rotational symmetry. And we call this G-steerability. All right, so my talk will be split into 3 parts. The first one is about images on Euclidean spaces. So you have a flat space, either a plane or volume or higher dimensional. And there we are looking at active transformations of the signal. Then I will come to the second part, which I call data gauges and gauge-independent networks. And this will take a different viewpoint on the same thing, where we look at kind of passive transformations, which means the signal itself doesn't change, but how you represent it numerically will change. I guess it will become a bit more clear later. And then the third part, we will generalize these convolutions on Euclidean spaces to arbitrary manifolds. All right, so first we have to talk about the symmetry groups we are considering. And we are looking at so-called affine groups, which always have, so they are a so-called semi-direct product of a translation group. We always have translational symmetries. And then in addition, we have this product with a group G, which is a subgroup of the general linear group. And this describes local symmetries like rotations or reflections, shearing of the image or scaling or something like that. And this group has a canonical action on the image plane. And since we have, it's split in a translation and this G symmetry, and then we can always write the group element as TG. And it acts by basically translating a point and before rotating or scaling it or something like that. And this is obviously useful if you have such biomedical imaging tasks. And yeah, we want to define convolutions which are not only translation equivariant, but affine group equivariant. And the question we have to ask here is now, okay, we need some affine group action on the feature spaces. This is what we need to define first before we can derive layers which commute with this group action. And yeah, we are defining our feature spaces as spaces of so-called feature vector fields, which are more or less like feature maps. So we have a c-dimensional feature vector associated to each point in d-dimensional space. But they have in addition a geometric type, which is a representation of the structure group G. And this just tells you how feature vectors transform if you rotate your image or so. And formally, you would describe this as a so-called induced representation. So you have this induced representation of rho, which is a representation or group action of the affine group. And it acts basically by moving feature vectors around on the base space. So if you rotate your image, each pixel goes to a new point. But in addition, we have a row transformation of the feature vectors itself. And I will give some examples. So the kind of most trivial example is that of a scalar field. And what you have there is that the transformed field at point x is equal to the original field at TG inverse x. So this is our transformed field at the point x, and then we look up the feature value on the scalar value from here. And this is the first part, this moving feature vectors on RD. But I said there's a second part that we have a row transformation, and in this case it's just trivial. So we would have a trivial representation which multiplies by 1. And if you look at the vector field, then again the transformed vector field would move vectors spatially. So they move from down here up to here. But in addition, you see that the feature vectors also rotate themselves. And to model this, we have to multiply here with G. So this is an action on the feature vectors themselves. And in general, if we have a feature field of type rho, we just have the same spatial transformation, but the feature vectors are being acted on by rho of G. Rho of G is just some group action of the symmetry group G. And you could pick something like, well, if you have a trivial representation, you get a scalar field. If you have the defining representation of the group, you get a vector field. But if you have the adjoint of the defining representation, you would get a co-vector field or one form, or you could have tensor product representations, then you get tensor fields. And this is all described by this mathematical framework. And this is what you also would have in physics or differential geometry.
Was that last slide important? Because I found it quite hard to follow.
Yeah, yeah, you can ask some questions.
Okay, so what's, just to get symbols straight, so what's G? That's a group on the image space, for example.
Wait, let me go one slide back. So our symmetry group is this affine group of G, which consists of translations and then these local symmetries, which would be rotations or reflections or so. And you can choose G. So in many people just look at, let's say you have images, you want rotation equivariance, and in 2D you would have that G is SO2, the rotation group. In 3D you would have SO3, or if you would have rotations and reflections, you would have O2 or O3. Yeah.
So, yeah, but this includes things like perspective transforms or not?
I'm not sure. So perspective transform would.
I'm pretty sure that.
Yeah, is it?
It's not fine, but it's like a, yeah.
Yeah. Yeah, we can look at it later, but G is for us just a subgroup of the general linear group. So the general linear group in D dimensions consists of D by D matrices, which are invertible.
Okay, so the invertibility, that was being marked. Yeah. So TG needs to be invertible. So where does
this holds in general for groups? Yeah. Okay. So group elements are always invertible. Like a rotation, you can invert.
Yeah.
Yeah.
So the idea is that you definitely want translation. G.
We always have translations, and G you can choose how you want. You can also use the trivial group, and then you will get a standard CNN. Okay. But if you use a non-trivial group, you have to choose here this group action row. And yeah, for a standard CNN, you don't have it since it doesn't have any specified transformation behavior if you rotate your image or so. But we want to be equivariant with respect to such transformations, so we need to define a group action first.
So rotate one of these translations and output, say, generally an output generated like
this row, yeah. So row text that would not be a translation, but something like a rotation or so. Yeah. Yeah, and then it outputs some matrix which tells you how to transform feature vectors. So let's say you have well, the scalar field is trivial. It always outputs a 1 since the scalar doesn't change. If you rotate a scalar, let's say a temperature value, and you rotate the temperature field, then the temperature value doesn't change. That's a trivial representation, and it would map to GL in R1, and it would just be trivial, not do anything. But if you have a vector, then the vector moves to a new position, but it also rotates itself, right? Yeah. And this is modeled by this representation G here. And if you would have a matrix, you know it, maybe if you have a change of basis in a matrix, then the transformed matrix is G, M, G inverse, right? And this would also correspond to some tensor product representation in that case.
So on the right, the input to G is the same rotation, but the output is a different group action, because in the first case on the right in the picture.
Where you mean here in the picture, or these two here? Yeah.
So am I right in saying that the input to G is the same in both cases? It's just a rotation.
So what we're looking at is transformations of feature fields. So, or feature maps, we could also say. So you have your feature map, and you want to know, okay, how does it transform if you rotate it? And so what you have in a group action is always you have something to be acted on. That's our feature field. And you have a group element which is acting on it. And this group element would be a translation and rotation, for instance. So this TG. And TG would act on the feature field and tell you how it is being transformed.
And is row something we need to learn? Or?
Row is a group representation. And yeah, that is something which is important if you're considering symmetries in general.
So D here is going to be the size of the feature vector. So it could be the whole image.
So RD is the image plane. So if you have images in 2D, we would have R2, but if you have volumetric data, you would have R3. And yeah, it's the spatial dimension. So it feature maps basically assign a C-dimensional feature vector to each point in RD. And C is the number of channels. This is why we call it C. You know, if you have feature maps, you have like a certain spatial resolution, but you have a number of channels. So you could think about it as C images, or instead you could look at view it as having at each point in space a C-dimensional feature vector. All right. Okay, so what I described before was a single feature vector field. But we are looking at a stack of multiple feature vector fields. This is similar to having multiple feature maps in a standard convolutional network. So we don't only want to have one feature, but multiple features. And this is formally described by this direct sum of multiple feature vector fields. And they transform according to the direct sum of representations, which means that if you have here 4 fields of types row 1, 2, 3, and 4, you build this block diagonal matrix. And you stack these feature vector fields on top of each other. And then as a whole, this transforms by, for instance, translating and rotating the whole thing. but then row 1 acts on the first feature vector field, row 2 on the second one, row 3 on the third one. But these different fields don't mix into each other. So you could have something like, let's say you do some weather prediction task and you have temperature, pressure, and wind speed. Then you would have a stack of 2 scalar fields, temperature and pressure, and a vector field. Or in medical imaging, you could have tensor fields or so. In diffusion tensor imaging, you would have also a certain field type. And this formalism tells you how these fields transform, and it can take these symmetries into account.
What do you mean by field? Like field of real numbers?
Feature field. This is another word like feature map, but in addition, we have this transformation law under the affine group.
Feature map after the transformation.
No, it's so. So a feature map is basically it's basically a function also from RD to RC, but it has only a transformation law under translations, but it doesn't have any transformation law under rotations or reflections or so. This wouldn't be defined. It's just not defined how to act on it. And we call it feature field if you also have an affine group transformation defined on it. So it's just like a feature map, but with an affine group action defined on it. And yeah, we first have to define the feature spaces, which are spaces of feature fields, before we can start talking about equivariant layers. Yeah.
These Fs are just matrices.
No, these are just, you can think about it like feature maps. So you have multiple feature maps. Here you would have 2 plus 3 plus yeah, 8 channels. It's a feature map with 8 channels, but it is geometrically split into the first 2 belong to one feature field. This could be a vector field. This could be a scalar field. Then here you could have, I don't know, matrix field or so.
And then what does it mean to put them in the brackets?
So the first feature field F1 transforms according to row 1. The second feature field F2 transforms according to row 2. So this just shows you how feature fields transform. And before I showed you how a single feature field transforms. And here this shows you how a stack of multiple feature fields transforms.
Okay.
And what I tried to show with it is that F1 transforms according to the induced representation of row 1, which means it rotates spatially, and then row 1 acts on the feature vectors on these 2 channels and kind of mixes them in a certain way. And then row 2 acts on this channel, row 3 acts on these 3 channels. Yeah. But all you need to get is that we have some transformation law defined on our feature spaces. Yeah. Oh yeah, and what I still wanted to say is, so usually if we design a convolutional network, we specify a number of channels in it. So we say we have, if we have a convolution operation, we say, okay, we have 10 input channels, 20 output channels. But in our feature vector spaces, we say we have certain field types. So like 10 scalar fields, 20 vector fields, and so on. And then every operation we are doing needs to respect these field types and transformation laws. And then the whole thing is equivariant. So here I have some examples. For instance, if you have an RGB image, you would have 3 channels. And these 3 color channels actually correspond to 3 scalar fields. Since if you would rotate your image, then these 3 color channels wouldn't mix into each other, right? So we have 3 scalar fields here. And then we could take each color channel and take a gradient operator on them. So we get a vector field for each color channel. And we could do it on the non-transformed and on the transformed image. And then we would have 6 channels on each side. And now we could ask, okay, how do these 2 things transform into each other? And we would basically have here 3 vector fields. So if we rotate the whole thing, then these channels here mix like vectors, which is a multiplication with this representation G. Then these 2 channels are vector fields. So we have this block of G, and also the last 2 are being transformed by G. And if you would have in addition now a scalar field on top, you would have a 1 here. And yeah. All right. So we view neural networks as a sequence of layers. And then an equivariant network can be built as a sequence of equivariant layers. And if if a single layer is equivariant, or each single layer is equivariant, then by induction the whole thing will be equivariant. So this is how we are going to build it, and from now on we only have to look at one single layer and make it equivariant. All right, and in our specific case, we have spaces of feature fields. So we have square integrable functions from Rd to Rcin. So we have Cin input channels. Then we have feature fields with Cout output channels, and our input and output fields are being acted on by this induced representation of rho in and rho out. So we can choose different representations, like, I don't know, scalar fields, and here we could have a vector field, and then actually as a solution, this layer would become a gradient operator, for instance. And the approach we are choosing is that we start with a flexible ansatz. So for instance, we could say we look at an arbitrary linear map, but then we demand affine group equivariance. And as a result, we will get certain constraints on our linear map. And for the affine group equivariance, we will always get spatial weight sharing. This comes from the translation equivariance. And in addition, we get G-steerability, which is a constraint on the convolution kernels, for instance, themselves. So some G-symmetry constraint. So the most important operation are convolutions, and we can derive them as a linear map, which you could, for instance, model as an integral transform, like here, so this integral transform would compute an output feature vector at position x by integrating over the whole space and accumulating these feature vectors, input feature vectors at all positions y, with this kernel k of xy, which takes these 2 points x and y, and to each point associates a matrix. And this matrix takes the C-in dimensional feature vector from point y and gives you a C-out dimensional output feature vector. And then to get the output at x, you integrate here over all y, this k of xy, f of y, which will give you one output feature vector at x. And this is a very general ansatz. It's not the most general one, but it's quite general.
What's
and
ansatz?
Ansatz means that you have some approach, some I don't know, it's a German word and you use it also in mathematics, but it basically means that you have a very flexible model with which you start, and then you get certain constraints from the mathematical structure you put on top of it. So this is just a general linear map, which would be kind of like an MLP being applied to your image. But now we demand affine group equivariance, and then we get certain constraints. So you can't use any integral operation here. But we have these two constraints. The first one is it needs to be a convolution integral. So we have this 2-argument kernel k of xy, but actually this operation has to correspond to a convolution with a kernel k of x minus y. So this kappa of xy has to be kx minus y. And this tells you that instead of looking independently at 2 points, you can only attend to relative distances, which is kind of what you also have in special relativity, in that you can only look at relative events in space-time. And this comes from the translation equivariance. So with this translation equivariance, we can derive convolutions. But in addition, from the affine group equivariance, we get a constraint on the kernel k itself, which says that it has to be G-steerable. And it's not too important what this constraint means here, but it's some linear constraint on your kernel. And you have to solve it. To do this, we observe that the set of convolution kernels forms actually a vector space. So you can take 2 kernels and linearly combine them, or you can scalar multiply kernels, so it forms a vector space. And this constraint is linear. So the space of steerable kernels is actually a linear subspace. Therefore, we can parameterize these kernels by solving for a basis of these G-steerable kernels. And then we expand the general kernel in terms of this basis with learnable weights. So instead of having our kernel directly parameterized in a pixel basis, as you know it from convolutional networks, then running your convolution, we have a basis of steerable kernels. And then we sum them together with learnable weights in each forward pass. And then we perform the convolution operation. And this is just a small overhead, so you wouldn't really feel it in practice.
What do you mean by G-steerable kernels?
Yeah, it's a kernel which satisfies this constraint down here.
Okay.
It's just some G equivariance or G symmetry constraint.
But what's a good real-world analogy of that?
I will show some pictures. Maybe it becomes more clear then. You also have a question? You mean this constraint here? Yeah, so this here means that you would spatially rotate your kernel or so, and then the spatial rotation of the kernel or whatever should correspond to taking the kernel and then acting on it as a matrix with this tensor product representation, which depends on row in, the input field type, and the output field type row out.
So the G-Steerable kernels just a space of sort of like rotational kernels that we multiply to with one another.
No, you don't multiply them with each other, but it's just your convolution kernel. But it has a certain symmetry inherent in it, which guarantees you that, like if you transform your input, your output will transform the correct way.
Okay, no,
right? You want equivariance, which means your input is, let's say, a scalar field, and you want the vector field as an output. Then there are only certain kernels which satisfy this property.
Oh no, okay, this makes a lot of sense.
Yeah. Okay. Yeah. I actually want to skip over that, but maybe we should shortly discuss it. That's an example of reflection steerable kernels. So here we look at reflection equivariance. And you see that all these kernels which you see on the right, so they are matrix valued, which is when there are multiple kernels sometimes. But they all have a certain reflection symmetry inherently. And this reflection symmetry depends on the field types. So here we have a trivial representation or scalar fields, a sign flip representation, which is also one-dimensional, but it basically tells you, so in physics you would call it a pseudo scalar field, which is a field which, if you reflect it, then it changes its value to the negative. And we also have regular feature fields, which for the reflection group would have two channels. And if you reflect your image, these two channels would also swap. And then we also have, so we have these three fields as inputs and then three field types as outputs. And this here would, for instance, tell you, okay, if we want to map from a scalar field to a scalar field, our kernel has to be symmetric. If we want to map from a scalar field to a pseudo-scalar field, we need to have a anti-symmetric kernel. And that makes kind of sense, since, like, think about a scalar field, it doesn't change if you reflect it. And you want to get a scalar field again, which doesn't change if you reflect it. This means that your kernel has to be symmetric under reflections, right? If you take such a kernel and you apply it to a reflected image at the same position or the corresponding position, then since the kernel is symmetric, it gives the same output. And this one, if you reflect your image and your input doesn't change, since this kernel is anti-symmetric, it will give you exactly the negative output.
This is like a really good example. It's like makes a lot of sense now.
Yeah, perfect. Okay.
So is this also sort of like manifold independent, because it seems like it would sort of like depend on the sort of like symmetries that would exist within the manifold?
Yeah, I will come to manifolds later. Maybe let's wait till then.
Okay.
But we will get very similar constraints. Yeah.
I mean, well, my questions related to this. These are still global transformations on like the future space.
Yeah, currently we are looking at global transformations. Yeah.
This is work globally, like sort of patches.
Yeah. So in practice, your kernel anyways just sees a local field of view. And then if you would have two independent field of views and you would transform them independently, you would get independently equivariant transformations, which is not, so intuitively this is clear that it happens here, but it's not captured by this mathematical framework, and we'll look later at so-called gauge symmetries, and then this will actually be the case. But you can't describe it in this framework. Yeah, maybe still the third example, if you go from a scalar field to a regular feature field, your input doesn't change if you reflect it, but you want that your output has two channels, which is why we have two kernels. And we want that they swap. So they should permute these two channels. And then our constraint is that we have an arbitrary kernel, and the other kernel needs to be a reflected version of it. So if you reflect your input, you get the same response, but in the other channel. And then, for instance, from a sign flip field to a regular feature field, we would have an arbitrary kernel, and then it's flipped and negated version. So you can solve all these constraints, and then you know what your space of reflection steerable kernels would be. And we actually have we have a theory for compact groups, so rotation groups or something like that. and that is a generalization of the Wigner-Eckert theorem from quantum mechanics. Yeah, it's quite interesting that we get exactly the same solution. That was worked out mainly by Leon Lang and Gabriele Caesar, who were master students of mine. And yeah, so what this theorem tells you is how to construct an arbitrary G-steerable kernel from harmonics, from harmonic functions. So for instance, if you have an SO2 steerable kernel, rotation steerable kernel in 2 dimensions, it would tell you which harmonic frequencies or which circular harmonics can be in this kernel and which cannot be in this kernel. And in 3D, you would have these spherical harmonics which play a role.
Maurice?
Yeah.
So there's a question in the chat that is,
yeah.
Is it the case that the individual kernels are G-steerable, or is it that the basis is G-steerable?
So it's a linear constraint. Our basis is G-steerable, but then if you linearly combine it, it will still give you a G-steerable kernel.
Okay, thanks.
Yeah. All right, so we are looking at these integral transforms, but they are actually not the most general linear maps. So if we want to go fully general, we have to look at Schwarz distributions, and you will get distributional convolutions. And that's, for instance, interesting if you want to cover something like steerable partial differential operators, which Eric Jenner worked out also in a master thesis. And yeah, so here's just an example. If you would want to map from a vector field to a scalar field in 2 dimensions, you could do it with the divergence operator or with the 2-dimensional curl operator. And in addition, you could multiply actually any polynomial of Laplacian operators to it. So this is what we figured out, and it gives you the most general partial differential operator, which maps between certain field types. Yeah, I just want to give a second example of a map from a steerable CNN. So we could look at bias summation, and then our flexible ansatz in this case would be a summation of a bias field, where we could think about summing a different bias at each spatial position. And then if we demand affine group equivariance, we will again get these 2 constraints. The first one is spatially, that it's spatially constant. So actually you have to sum the same bias at each position, which is what you're doing in a standard convolutional network. And then also the bias has to be G-steerable or G-invariant, which means that the bias vector has to be invariant under this row of G action. And yeah, we have similar results for equivariant nonlinearities or pooling operations. So each of the operation you use in your steerable CNN has to be somehow spatially shared and G-steerable in a certain sense.
What is a bias field?
A bias field is just yeah, a square integrable map from RD to RC. So it's yeah, just a field of biases, but you could have a different bias vector at each point. And then from the symmetry constraint, we get that you can only use the same, you have to use the same bias at each position. Okay. Since otherwise, if you would translate, then you would suddenly start summing different biases to different positions. And yeah, it has to be spatially constant in order to be translation equivariant. Yeah. All right, so we have actually a library. If you would want to use this, it's quite hard to implement yourself, since you first have to understand all the representation theory and then code it all up. So it's maybe easier if you use our library. And what I have here are just 2 short code snippets. The first one shows you how to instantiate the convolution in PyTorch. And here you would essentially just pass a number of input and output channels. And what we do in our library is we define a symmetry group and its group action. So here this w.r.t 2D on R2 would be rotations of the image plane R2. And this n equals 8 means that we consider the symmetry group C8, or yeah, which would be rotations by multiples of 45 degrees. Then we need to define the input and output feature field types. So for instance, here we would have 3 times the trivial representation, which means 3 scalar fields, which you would use for an RGB image. And as output field type here, we would have 10 times the regular representation of that symmetry group. But you can use anything. So you could also have here certain scalar fields, vector fields, tensor fields, whatever you put in there. And then you define your field type of the whole feature space. And then our convolution operation is instantiated by passing the input and output field types instead of the input and output channels. And internally, this library will then construct the most general complete basis of G-steerable kernels for these field types. So you don't have to think about all the representation theory, it's all in the background. Yeah, I will show some empirical results. Actually, not too many. I had some biomedical imaging results before, which are quite impressive, since there you really have these rotational symmetries and so on. But we even have improved performance on natural images, which don't have rotational symmetries. It still works better somehow. And we didn't even do hyperparameter tuning. We used a wide ResNet architecture and just plugged in our convolutions instead of standard convolutions. And then we did this on Cypher 10, Cypher 100, and STL10.
What's STL10, sorry?
It's very similar to Cypher 10 and 100. It has 10 classes, but the images are bigger, 96 by 96 pixels.
Okay. For your manifold data set, how big it is, what network you used?
Yeah, there are many different results. What I showed in the beginning, this segmentation task, right? So this was a scan of an electron microscopy scan of a brain of a fruit fly, and we should segment the cell boundaries. I can't really tell you now how big the dataset was. There's actually in 3D a very nice evaluation by Taco Cohen and Maurice Weiler, one of his students, and they got very impressive results where they had like with an equivariant network a better performance with a 10 times reduced dataset size.
Okay, what are the baseline networks that you're using?
So what works best usually is if you use these regular representations of the group, which corresponds to group convolutions. I don't know whether you heard it before, but this works best in practice.
So what's your baseline? What's like when you're comparing against standard CNNs? So
Standard CNNs, yeah, I'm not really sure which baseline we used.
are they like ResNet 50s, ResNet 100s?
The issue is that we are usually, so we are more parameter efficient, which means we can scale up our models, and at some point they don't fit into memory anymore. So we are probably comparing with smaller networks than ResNet 100s, but you could do it in principle if you have enough compute power. And it really scales. Like we didn't see that it saturates at some point, it just works better. Since we are more parameter efficient, we get a constraint on our kernel space, so we have less parameters, which means you can scale up your model like mad. We had actually a model on the rotated MNIST dataset, which is a benchmark dataset for rotation equivariance. And there we had like 1,500 channels or so on MNIST, which still improved performance without overfitting. So you can build huge models this way.
Okay, so you compare like CNN with set number of parameters with your model.
Yeah.
That's the direct comparison.
Yeah, it's not really clear what is most fair, but we have comparison where we have the same number of channels, but then we have less parameters, the same compute. And if we choose the same number of parameters, we have more channels, and we compared with both just to keep it fair. And well, both work better, as you see here, and it's actually a quite impressive improvement since these are natural images which don't even have rotational symmetries. And we improved from 17.1 to 15.6, and then even further to 14.3, just by plugging in our convolutions.
Also,
Yeah.
you've tested this sort of stuff on things like sort of like 3D modeling of proteins as well as
Some people did, we did not ourselves. Yeah. Yeah.
Another way to do that is to do
Mm-hmm. Yeah, good question. So if this would work as well, then you could also just go and take an MLP and process images and feeding in translated images, right? But somehow CNN is better as an MLP with augmentation, and it's the same here. So our steerable CNNs are better than standard CNNs with rotational augmentation. And the reason is that if you augment, then your model is still not constrained. It still has to learn the symmetry and doesn't, so it has much more parameters.
Yeah,
Where we enforce it from the beginning, and then our model cannot overfit. Mm-hmm. Yeah.
Have you tried any adaptive convolution convolution baselines, like deformable coordinates or something like that? Like, so people using computer vision.
I think you could combine it in a certain way, but no, we really only looked at this comparing with standard CNNs or ResNets or so.
You have a better like pixel adaptive convolution, or they look at specific parts of it, they're trying to transform it around. So sort of
No, we didn't do that. No. Yeah.
In the code snippet, I think you specified one of the parameters is like the degrees of symmetry for the rotation.
Yeah.
Is that an important hyperparameter? Because I guess with translational symmetry, translation is discrete on pixels.
Yeah, right.
Rotation feels somewhat different in that it's usually we want continuous equivariance in rotation. Is there some intuition for why discretizing it still works?
So we can also work with continuous symmetries, but then we can only use certain field types, like irreducible representations. I don't know whether you know what that is. But yeah, we can only use certain field types, but not the regular representation, since this would, like if we have a discretization in like n angles, then we would have n channels, which would somehow permute then in a certain way, which is described by this. And actually the performance becomes better if you increase n up to a point where it saturates at, like, I would use 8, maybe up to 12 or 16, it still improves, but then it really saturates. And if you would scale up to SO2, which is kind of the continuous case, you would have to use infinitely many channels.
Right.
So either you discretize it or you use a different field type. But these regular representation of discrete subgroups of rotations usually work best.
Yeah. There is I think you kind of implied there is some notion that you could have continuous.
Yes. Yes, it works. Yeah. Also with translations actually, but then you have to define your signal also in Fourier space, right? And then you can have, if you have a signal in Fourier space, let's say it has only one frequency, a certain frequency, and then you can you can decompose it into a signal of a certain frequency just has a phase shift. Basically, that's the only information you have. And if you then have a basis of a cosine and sine, for instance, any linear combination will kind of shift this cosine and sine around. And then you get, with these two channels only, you would get continuous translations. And you would get something similar, but with these harmonics on the with these circular harmonics.
But doesn't this sort of like discretization of the space still impact your performance? Say, for example, even if you shift into Fourier space, you'll sometimes do like fast Fourier transform. That's still all.
Then you have a discretization of frequencies, and you would essentially look only at a subset of frequencies, right?
But usually, so for example, what happens if you're dealing with an irregular grid or discretization?
So you're talking about the translation equivariance now, or rotation equivariance?
Both, because I'm wondering if it's discretization invariant.
Yeah, that is indeed the problem. So theoretically, we just formulate everything in the continuum, but yeah, you have to investigate what happens if you discretize it, and certain discretizations might work better than others.
Yeah, because one of the papers, the foreign new operator paper, will argue that sort of like it's discretization invariant, but there's an underlying assumption that you're dealing with a regular grid. But once you start shifting to an irregular grid, all of a sudden it kind of like pulls up a huge number of sort of strange sort of problems, even if you're dealing with sort of like strange like spherical grids.
Yeah, I guess what you have to look at there is that you have a certain cutoff frequency. So at least for a regular grid, you have this, I think it's called Nyquist frequency, like the highest frequency you can represent before you get to aliasing effects. And if you have an irregular grid, it's probably harder to describe, but something similar like aliasing will probably happen. Yeah. All right, so this was about these natural images, and then what is from a theoretical viewpoint actually more interesting. You can't see it too well probably, but it's this big benchmark table here where we test different groups, then different representations, different equivariant nonlinearities, and maps which we classify in the end. So we want the whole thing to be invariant. So we have also different invariant maps, and we just benchmark all of these different choices you can make in our framework. And in particular, we re-implemented lots of prior work. So for instance, Daniel Worrell had his harmonic networks, or then we have regular group convolutions and all these things. And in our library, you can implement all of it, and you can even mix their field types.
We've also got one question in the chat.
Yeah.
They're asking, Imraj is asking, does this have implications for invariance rather than equivariance? How would this task, how would this help tasks like classification?
Yeah, so invariance is actually a special case of equivariance, where the group action in the output is trivial. So you can have a trivial group action which just says, okay, if your input rotates, then your output does not change at all. And this is what we always do in classification tasks. Yeah. All right, and this is just a visualization of an SE2 steerable CNN. So we have rotational and translational symmetries, and we have a standard CNN, and we feed in a rotating input. And then we get, of course, a rotating output. But if we rotate it back and stabilize this viewpoint for our equivariant CNN, you see that the output is quite stable. It fluctuates a little bit due to numerical noise, but it's quite stable. While the standard CNN just gives a completely undefined output. It just transforms without having any guarantees on rotations. All right, so I will come now to this passive viewpoints or gauge transformations. Actually, that's pretty close to Einstein's principle of covariance, since he said the universal laws of nature are to be expressed by equations which hold good for all systems of coordinates. And what we would argue is that also the laws of AI should be coordinate independent. And I will start with a toy example, which you probably know from everyday life, which is the example of gauging a weighing scale. And the point there is you want to measure a certain mass. And if you want to implement a neural network which has physical mass as an input, you need to represent it somehow numerically. And the mass itself doesn't have a numerical value attached to it. And what you do is you measure it relative to some choice of reference weight. So you could say, okay, I measure it in terms of kilograms. And this would be a gauge map formally, which takes this scale-free physical mass and maps it to positive real numbers to some numerical weight value. And this kind of gives you axis ticks on this positive real line. But of course, you could also use different units of measurements like pounds, and then you would get different axis ticks. And it really doesn't matter which one you choose, or it should not matter at least. And in particular, you get unit transformations, or more generally, we talk about gauge transformations between these different units of measurements, which in this case would just be this gauge group element would just be a multiplication with a positive real number, which just scales the grid accordingly. And what is really important to understand here is that these gauges you choose, they should be equally valid, but often we have the case that there are certain gauges which are preferred by the mathematical structure of the problem. And this in particular also determines the gauge group. And in this example here, we measured weight relative to a measurement, to a reference weight. So basically these gauge maps are linear maps here. And then also the unit conversion will just be a multiplication with a positive real number. But you could think about taking a different gauge, which just is a nonlinear function, and then you have these nonlinear axis ticks, and your gauge transformations would then just be diffeomorphisms. So these choices of subsets of preferred gauges and gauge transformations, they are closely related to each other. And what is more related to what we talked about before is the example of images on some Euclidean space. And here we distinguish now between Euclidean affine spaces, which are like a Euclidean vector space, but they don't have any coordinates associated to it. So we shouldn't think about images living on RD, but actually on a Euclidean affine space which doesn't have any coordinates or no choice of origin. And if we want to in a computer we need to choose a pixel grid, or we need to represent it somehow on R2, for instance. But if we do this, we actually make an implicit choice, which we never think about usually. But implicitly, we have a coordinate chart which maps our coordinate free space to a coordinate representation. And sometimes that's unique, but for instance, if you have a biomedical image, then you could record it from all kinds of rotations or different translations. And the pixel grid or chart you choose is really a choice which is being made. And you have to be aware of that. And of course, you could again choose a different coordinate chart or pixel grid. And then you also get a gauge transformation between them. Or chart transition map, it's called in this case. And again, we can have a certain geometric structure in our task or on our image, which gives or allows us to restrict attention to a certain subgroup of or subset of charts, which then also transform according to a subgroup of gauge transformations. So since these Euclidean spaces are always affine spaces, which means that they preserve, or they have a notion of parallelity of lines, these maps should always preserve that. So then we get here affine maps as charts, and we get affine groups as transformations between these charts. But often we also have a metric given. So we have a notion of distances and angles on our image. And then we can demand that these maps here should preserve distances and angles. So we have actually isometries as charts. And then also the chart transition will be isometry group of a Euclidean space. And then you could even go a step further and have a natural image where you have a preferred notion of up-down, or maybe also left-right. And then you could restrict here to charts which preserve this notion of up and down direction. And the only ambiguity would then be in the choice of origin. So you would have still here an ambiguity of translations in the pixel grid you choose. And this would actually correspond to a standard convolutional network, but viewed from a gauge theoretic perspective. Okay, so this was just how we would describe a single image, but of course we are looking at maps between images. And yeah, here I have, it could be a convolution operation. And we should really think about it in a coordinate independent or coordinate free way, that we map between these coordinate free representations of the images. But if we implement it, we have to represent that operation relative to coordinates. So what we do is we take our input image represented in the chart, we have our output image represented in the chart, and then the coordinate representation of this map L is LA, and LA goes from here to here, so it's just XA inverse, then L, and then XA. But we could, of course, choose a different chart. Then we get this different representation LB, and in particular also these transformations between these different representations. And so coordinate independence just means that whatever we are doing should be independent of the charts we're using. Our neural network should never depend on the choice of chart. Of course, you will get a different numerical representation out, but they are equivalent. You can always transform back and forth. So in this sense, it should be independent. And if we look now only at the outer square, it looks almost like an equivariance constraint, right? But the difference here is that we have a different function LA and LB at the top and bottom. And for equivariance, you would have the same function. So this is really only coordinate independence until now. But just assume that you have given an image in with a certain choice of pixel grid or chart, and then you want to apply a neural network to it. Then you have to make sure that this application of the neural network has to be independent from this choice of chart. And usually you don't know which chart was chosen. So for instance, you have a satellite image or biomedical image and you don't know in which rotation it was recorded. And then you have to make sure that whatever you're doing is independent of this choice, which kind of means that the operation has to be the same in both charts, or LA has to be equal to LB. And if we set LA and LB equal, this actually becomes an equivariance constraint. So then the coordinate independence, if we also have weight sharing over different charts or gauges, becomes an equivariance constraint. And for this example here, we would actually again get spatial weight sharing and G-steerability. So we derived again these steerable CNNs, but not from a viewpoint of actively transforming our signal, but now from passive transformations of the coordinate charts. And if we are looking at general manifolds, then we actually have to look at local reference frames and local gauge transformations. And this is what I will come to now. But yeah, I think time is running out a little bit. Or should we do it?
I think.
Should I just go on? Or?
Yeah, I think you can go on, and if people need to
Okay.
leave, like they can leave.
Yeah, perfect. Okay. Yeah, everyone can leave if you have a meeting or something. Yeah. All right.
Thank you very much.
Yeah, thanks. All right. So we're looking now at signals on manifolds and convolutions on manifolds. And yeah, some applications would be segmentations of meshes or shape correspondence stars, or yeah, so the metric tensor field on a manifold is actually also yeah, a specific type of feature field. So you could even try to predict the metric of a manifold to predict, I don't know, deformations or so. Then Pim de Haan from our work group had a nice application where he used these meshes of an artery, and he predicted the wall stress on these arteries. Then obviously in general relativity, we are considering pseudo-Riemannian manifolds in that case, and you could also try to define convolutions on space-time. And of course, Euclidean spaces and spheres are also special cases of manifolds, so our theory should also cover Euclidean convolutions or spherical convolutions. And what is important to understand is that we are defining our convolutions in the intrinsic geometry of the manifold and not in some kind of embedding space. So for instance, if we have the spherical CNN, you could embed it in R3 and then convolve in R3, but we are really convolving in the spherical surface. So everything what we are doing is intrinsic. All right, so to define convolutions on manifolds, we have to think about some design questions. The first one is what are our feature spaces? And we are again using feature fields, which pop up now from a different viewpoint. Then we have to think about how to define a convolution kernel on the manifold. And the issue there is that you have a different geometry at different points of the manifold. So it's not obvious how to share weights between different points. But what we are doing is we define the kernels on the tangent spaces, and then we map them down with the exponential map, which is what you see on the top image. Then we still need to know how to share weights between different tangent spaces. And this actually requires G-steerability again. So the same constraint will pop up. And finally, we have to look at isometry equivariance, which means that if your manifold has a certain symmetry, then your convolution operation should commute with this symmetry. All right, so we can brainstorm a little bit about how to share weights on manifolds. What we are doing, or what we saw in the case of the Steerable CNNs was that we used the global transitive symmetry of the space in order to share weights. And yeah, transitive symmetry means that your group action can actually move any point to any other point. So if you have translations on a plane, you can move any point everywhere else. Or on a sphere, you could take the North Pole and rotate it everywhere else. And such spaces are called homogeneous spaces, and there you can define convolutions that way. But if your group action is not transitive, like this egg, then you can only share weights on the symmetry group orbits, which are these colored rings. So you would get the same kernel on each orbit, but between different orbits, you wouldn't share weights. And if you have a completely asymmetric manifold, then you don't get any weight sharing at all this way. So it's not a useful approach for us. Then a different intuition which many people have is that if you convolve, you take your kernel and you shift it over the manifold. And this is actually well defined on Euclidean spaces, since paratransport is path independent on Euclidean space. But if we go to a curved space like a sphere, then you will get a different rotation of the kernel out if you choose different paths. And if you would have a non-orientable manifold like the Möbius strip, you have this twist in the strip. If you go once around the strip, you will end up with a reflected kernel. So again, it's ambiguous. And actually it turns out that this choice of kernel alignment on the manifold is inherently ambiguous. You won't get around it. So we have to deal with it. And this is, again, something which will call for G-equivariance or G-steerability. And to formalize this mathematically, what we are doing is we identify the alignment of a kernel on a tangent space with a choice of local reference frame. So we have at each point P of the manifold, we have a tangent space which is called TPM, and these are vector spaces, and they don't come, usually they don't come with a canonical choice of reference frame, but we have to choose one, and if we choose, for instance, these two frames which are rotated relative to each other, then we get accordingly rotated kernels. So instead of thinking about kernels, we can treat it mathematically as a choice of frame. And this implies in particular that given the frame field, this and the kernel which we are sharing along this frame field, this gives us a kernel field, where a kernel field just means you have some kernel at each point in space. So for instance, if we have this standard or canonical frame field on R2, so actually on R2 you have a canonical choice of frames, then you would get this canonical frame field, which you use in standard CNNs. But you could use an alternative frame field and you would get this alternative kernel field. And I don't think anyone would use this. It's probably not practical, but you could do it in principle, and our theory describes it. And in particular, if we now think about the ambiguity of the alignment of a convolution kernel on the manifold, it's actually the same ambiguity as that of the choice of reference frames. And this is captured by what is called a G-structure on the manifold. So to understand what a G-structure is, we first have to look at the frame bundle. And the frame bundle, you can think about it as the set of all frames. So at each point you have a tangent space and all kinds of frames of this tangent space. And if you take them all together, you get what is called a frame bundle. So you have your manifold, and at each point you have you have like this fiber, it's called, which consists of all choices of frames at that point. And if you allow for arbitrary frames in the frame bundle, then the transition functions are GL devalued. So you have GLD is the general linear group, which consists of arbitrary invertible matrices. So yeah, these are the transformations between arbitrary frames. But often we look at a subset of geometrically preferred frames. So often we have a certain structure given on our manifold. And then we talk about the G-structure, GM, which is a sub-bundle of frames or subset of frames, where the transition functions are G-valued. And for instance, here, this picture actually shows only frames which are rotated relative to each other. And the transition functions here would take values in SO2 and not in GL2. And here are some more examples which maybe make it a bit more intuitive. My mouse pointer, okay. So this is the standard trivial group structure on the Euclidean space, but you could use a different one. This here is a reflection group structure on the Euclidean space, and another example of it. And you see the transition functions here between different frames, or here between the frames at one point are trivial. Here you have reflections. Here you have a rotation group structure or SO2 structure. Here you have a scaling group. Here you have a trivial group structure which corresponds to polar coordinates, and polar coordinates and reflected frames. Yeah, on SO2 you would usually look at this. Sorry, on S2, the sphere, you would look at an SO2 structure, since there are actually certain topological obstructions on the existence of certain G structures, which means that if you demand that your G structure is continuous, then you cannot reduce the structure group further than SO2 on a sphere, which is probably you heard about the Harry-Ball theorem. That's very related to it. And yeah, this is why if you would choose this trivial group structure here on a sphere, you get here at the north and south pole singularities, and you cannot get around that. And then also your convolution operation, which you described, would have discontinuities, which is probably not what you want.
Sorry,
yeah.
When you said the G structure is continuous, is that talking about that those north pole singularities? Is that
Yeah.
where that thing breaks?
Yeah.
It's like
So
frames at different points.
exactly, if you go along the manifold, the frames should change in a smooth or continuous way. Yeah. And yeah, it's a topological thing. So yeah, here this monkey head is topologically also a sphere, right? So the same thing holds. You need to have an SO2 structure if you want to have a continuous operation. And on the Möbius strip, that manifold is non-orientable, so there you need a reflection group structure, at least. So since just think about it, if you would just use one frame at each point, you could do that in a continuous way, go once around, and then you end up in a reflected way, and there you have a discontinuity. So you have to look at reflection group structures on non-orientable manifolds. Also, the Klein bottle would be an example where you need that. All right, so we have a G-structure on our manifold, and this kind of means that geometrically all these choices of frames are exactly equally valid, which means that whatever we are doing, any object or any morphism, which are maps between objects, have to be expressible relative to each choice of frame in our G-structure. And a simple example is that of tangent vectors. So if you have a tangent vector v in TPM, that is actually a coordinate-free geometric object. It doesn't know anything about coordinates. But if you want to implement a tangent vector, you need to express it in a basis to have numerical values which you can store on your PC. So you're choosing a reference frame to do that. And then, yeah, in this example, the coordinates would be 1, 1 for this vector v. And we would call it VA then, since we used gauge psi a. And psi is mapped from TPM to R2 in this case. And of course, we could again choose a different gauge p, and then we would get different coefficients VB, which in this case would be square root 2, 0. And of course, we have again gauge transformations, and they are G valued if we have a G structure. So this is what it means to have a G structure. And the important point is that VA and VB are different numerical values, but they represent exactly the same coordinate-free geometric object, just relative to a different frame. And coordinate independence means it doesn't matter whether you describe everything relative to frame A or B. Okay, and we do exactly the same with feature vectors or feature vector fields. And here we have that the numerical representations FA and FB, these are C-dimensional feature vectors relative to frames A and B, and they are related by this gauge transformation law, that FB is row of GBA FA. So if you transform your frame by G, then your feature vector will transform by row of G, which is exactly what we had before, but now from a local gauge transformation viewpoint. And again, if we have a trivial representation, we get the scalar field. For the standard representation, a tangent vector field, tensor fields. And we also look at irreducible feature fields for irreducible representations and regular feature fields and whatever you can come up with. And yeah, if you know about fiber bundles, maybe it's interesting to know that this corresponds in the coordinate free setting to what is called a G-associated vector bundle. So if you know about it, you will understand it. Otherwise, just ignore it and think about this thing transforms according to a row of G. All right, so these were objects on the manifold. But to build a network, we have to look at morphisms between objects or maps between objects. And a simple example is a linear map of vectors on the tangent spaces. And yeah, so such a linear map is coordinate free, but again, you can express it relative to gauge A, and then you get the matrix MA out, which represents this linear operation. Or you can choose a different matrix MB or different gauge B, and then you have MB as a matrix representation. And we have gauge transformations now in the domain and codomain. And you would have that MB is the same as GBA inverse, then MA, and then GBA. And this is how matrices transform, which you know from, let's say, some diagonalization of a matrix or so. Then you also have this left and right multiplication with these two matrices. And again, it doesn't matter which choice of coordinates we use to represent whatever we are doing. And to describe convolutions, we have to look at coordinate-independent convolution kernels. So here we are assuming to have some kernel given on the tangent space. It's just there for now. And then we can express it relative to frame A or relative to frame B. And again, we get a certain transformation law out between this kernel in gauge B and in gauge A, which is this constraint down here, which looks very much like a gauge or G-steerability constraint. It's actually almost this constraint, but again, with this point that KA and KB don't have to be equal. So it's up to now only coordinate independence. It tells you how these different coordinate representations relate to each other, but there's no equivariance constraint. But if you want to perform a convolution, you have to share this convolution kernel, and you don't know relative to which frame you have to share it, or in which gauge you have to apply it. And if this weight sharing process itself is to be coordinate independent, this basically means that yeah, the kernel should be the same in each gauge. So whatever gauge you choose, kx for an arbitrary gauge x should be equal to this shared kernel k. since otherwise you make an arbitrary choice. And if you do that, in particular, we have that Ka and Kb are equal to K, which you can plug into this coordinate independence constraint, and then we get a gauge equivariance or G steerability constraint out. So it's again the same thing we saw before, but now from a very different viewpoint. All right, so this gives us everything to define GM convolutions, where we are assuming to have a Riemannian manifold M given, and then we have a G structure GM on the manifold, and we also need to assume that we have a G-compatible connection, which defines you how to parallel transport feature vectors on the space, which you need since feature vectors at different points live in different spaces. It's like you have different tangent spaces at different points. In this case, we have different feature vector spaces at different points on the manifold. And the connection tells us how to transport over the space. And of course, we need a kernel which we share over these points to define the convolution. And then this convolution is performed by these two steps here. The first one is applying what I call a transporter pullback of the feature vector field. And this thing is, it's a more or less a pullback by the exponential map. So we have our kernel in the tangent space, but our feature vector field is on the manifold, and we need to project it up to the tangent space. And we do this by, let's say we want to have the feature vector value at the vector v. Then we take the exponential map of v. And this is basically going in the direction of v with the distance of v, which runs down here, takes this feature vector value and attaches it up here at this point v. But as I said, these feature vectors at different points on the manifold live in a different space. So we still need to bring it into this feature vector space at P. And we do this by actually parallel transporting this feature vector along this geodesic here of the exponential map back to P. And this operation mapping from the manifold to the tangent space is what I call a transporter pullback. And you can think about it as how a local observer at point P would see the feature field from his point of view. And then if we have our feature field on the tangent space, we compute an output feature vector at P just by taking this pullback and multiplying it with the kernel and then integrating this whole thing. And that defines our convolution. And yeah.
I'm just wondering, thinking about the G-compatible connection part. Can you
Yeah.
give an example of like a connection that's not G-compatible?
Yeah, I can give you an example. Let me skip ahead. Yeah. So if you have the Levi-Civita connection on the Euclidean space, you would just transport a vector as you think about it, just by moving it around. And that would work here for let's say you have only the red frames, and you move the vector around here. Then let's look at here this bottom part. You would move a vector around here. Then if you move from one point to another point, the transformation relative to this frame would be trivial, and we have a trivial group structure. But if you would move from here to here, you would, relative to the frame, your coefficients would change, which would be described by some group multiplication. And here you have only a trivial structure group, so you can't describe it. And then the only parallel transport you can describe in this frame field here is one where the feature vector actually moves with this rotation of the frame field. And I needed to include it like this since people are working with such frame fields on manifolds. So if you use, the Levi-Civita connection is always a connection which is compatible with the metric structure or orthogonal group structure of the manifold. So you will only have rotations, or if you have a Möbius strip, also reflections. And then this Levi-Civita connection is always orthogonal group compatible. But if you're choosing something like a frame field, a trivial group structure on a sphere, then you cannot describe the Levi-Civita transport. And some people are doing this. And yeah, to keep things general, I had to use this more abstract framework. And what I still wanted to say here is that we have to apply our kernel in a certain orientation, but since our kernel is G-steerable, it doesn't matter which orientation we choose. If we choose a different one, we just get an output which is transformed by rho of G. We transform our frame or kernel by G. All right, so this finishes up basically the convolution part, or the definition of convolutions on manifolds, but we still have to look at the isometry equivariance of this operation. And so in the first step, we will just look now at what I call a kernel field transform, which is more or less like a convolution, but for now without the assumption of shared weights between different points. So you could have a different kernel at each point of your space. And then we have this theorem, which says, okay, we're looking at the subgroup I of the full isometry group of this manifold. And then the kernel field transform is equivariant with respect to this subgroup I, which means that it commutes with this action, exactly if the kernel field you're using is invariant under this isometry action, which is what you're always finding if you look at equivariant networks. They always rely on some invariance of the neural connectivity. And yeah, in the example here of the egg, our full isometry group would consist of rotations and reflections of the egg, which is actually the right case. But if we look at the subgroup of only rotations, this would give us weight sharing along these orbits. So, yeah. And if we also consider reflection equivariance, we actually get a constraint of this stabilizer subgroup on the orbits. In this case, we would have also that our kernels actually have to be reflection equivariant. Okay, so now we can go back to convolutions, where we shared weights according to some G structure, GM. And the important isometry group here is what I call isom-GM. That's a subgroup of all isometries. And it's that specific subgroup of isometries which are symmetries of the G structure. So in this top example, this G structure is only symmetric under horizontal translations, but not under vertical translations. So isom-GE would be translations in horizontal direction. And in this second example, we would have full translation invariance and also reflections in our isometry group. And to understand now the equivariance properties of a convolution, the important thing to understand is that our G-steerable kernel field, so if we have a G-steerable kernel and share it relative to this G structure, will automatically be invariant under this group isom-GM, since yeah, it has just the symmetries of this G structure. And then you can, for instance, here use different frames which are reflected to each other, but due to the G-steerability, we have an invariance there. And yeah, so we have an isom-GM invariant kernel field, and this theorem from the last slide tells us that GM convolutions are isom-GM equivariant. And this is quite cool, since now you can just think about designing G structures if you want to design an equivariant network. So back to this slide here. Yep. This G structure here, or trivial group structure, is invariant under translation. So you will get this translation equivariant CNN out, the standard CNN. Here you will have translation and reflection equivariance. Here you will have translation and rotation equivariance. So these guys here actually all correspond to the steerable CNNs from the beginning of my talk. Yeah, and here you don't have any, so isom-GM would be trivial, so you don't have any isometry equivariance with this choice. Here also not, but you would have at least local reflection equivariance. If you use these polar coordinates here, then you would get rotation equivariance, but no translation equivariance anymore. Here you have rotation equivariance and reflection equivariance. Here you have SO3 equivariance. Here you have SO2 equivariance, rotations around the z-axis. Here you have a trivial isometry group, so you can't have isometry equivariance. And in the case of Möbius strip, the isometries of this G structure would be shifts along the strip and reflections of the strip.
Sorry, I just
Yeah.
on the monkey face thing. That wouldn't you still get the kernel being like, doesn't matter which choice you choose for faces, they're like rotation, so there must be rotation invariant.
You mean which choice of frame I use from this G structure? Yeah. So if you use a different choice, then you align your kernel in different rotation, and then your output feature value will be steered accordingly. So it transforms by row of G, but that contains equivalent information. Yeah. All right. I will actually skip in interest of time over the experiments and just very shortly show what we are doing there. So one toy model implementation, which is also available on GitHub, is these convolutions on a Möbius strip. And yeah, that's quite nice as a toy model, since it actually has internally a flat geometry. It's just connected at the two ends like a cylinder, but with this additional twist. And we implemented this, and of course we tested it on MNIST, but now it's Möbius MNIST, where if we shift the digit out at the right, it comes back in at the left, but with this additional twist. And if we have a standard convolutional network and compare it with this gauge equivariant or coordinate independent CNN, we see that our equivariant CNNs work better, and they are isometry equivariant, which doesn't hold for a standard CNN, which doesn't know about this flip symmetry. And yeah, in this case, we also have to use reflection steerable kernels, of course, these, which I showed you before. And we also implemented it on the icosahedron, which is a nice approximation of a sphere, and it's computationally more efficient since you have locally flat surfaces. So on each surface, we can actually apply a standard convolution operator. Or yeah, on these, yeah, always these four faces. If you cut it and flatten it out, you get this structure. And it also works better. Yeah, and on this slide here, I show the last part of my paper, which are actually like 70 or 80 pages of literature review, where I go over all kinds of Euclidean steerable CNNs, and then there are some of these punctured Euclidean CNNs, which correspond to polar coordinates of these hyperspherical coordinates. We have certain spherical CNNs, CNNs on arbitrary meshes, and also our Möbius convolution. And I really go in detail over all these geometries and all these different models and explain how they are described in our framework. So we have different choices of manifolds, different structure groups and G-structures, different global symmetry groups, different choices of field types or representations. And then you see all these things here are citations of different papers. And whatever they developed somehow fits in our framework if we make the right choices here. So it's very, very general, which is usually if you generalize things mathematically in physics, you always end up with differential geometry, and apparently it's the same in deep learning. All right, and to wrap things up as a nice overview, so we started out with active transformations, where we actively transformed our images, and we demanded equivariance with respect to that. Then we looked at passive gauge transformations instead, but still on a global level with these coordinate charts. Then on manifolds, we had to look at it locally. And we could still prove isometry equivariance, which kind of brings us back to the beginning. So that closes the loop.